Okay, so just to get started, how many people in the room currently identify as architect? Okay, how many people have that in their title somewhere? Smaller number of hands, that's cool. How many people are not an architect and don't really want to be one? Show of hands. Okay, why the fuck are you here? I mean, it's right there in the title, people. What I intend to do with this particular session is I want to go over distributed systems. I'm not really going to focus on promoting any one particular approach or any one particular technology, but what I really want to do is I want to try to elevate the conversation here a little bit. As architects frequently do, I want to try to abstract away a little bit and get a sense of what is it exactly that we're trying to do when we start working with distributed systems and whatnot. Real quick, hey, AV guy over in the corner, the timer here hasn't started yet, and much as I would love to believe that I have forever to talk, I'm pretty sure. Can you make sure the timer is running? It doesn't look like it started. There we go. Otherwise, these poor people will be here for 3 days, because I can, in fact, talk for 3 days. This is a known, proven fact. As a matter of fact, at one point during a birthday party a number of years ago, I was standing around with a group of my friends, and a couple of them wandered off, and after a few minutes, I glance over in the corner, and my wife is standing there with a number of the others, and they just keep looking over and laughing. And I'm like, what is going on? So finally, after a few minutes of this, I finally say, what is so funny? And they're like, poor Eric, the friend of mine that I've been talking to, you've been talking for 45 minutes straight, and he's not had to do anything except go like this. So believe me, without that timer, you would be here for the entirety of the conference, because I really could spend all day talking about this stuff. However, what I want to do is I really want to try to elevate that conversation, abstract it, and give us some tools, some means of analysis of thinking about distributed systems in a big picture. Now, anytime we start with this kind of a topic, one of the good things to do is to sort of establish our baseline. What is it exactly when we say distributed system? So, the formal definition of a distributed system: one in which the failure of a computer you didn't even know existed can render your own computer unusable. I realize it's after lunch and everybody's tired. That's a joke, people. Just so you know, right? Because I mean, really, that's not how distributed systems work in the real world, right? How many of you own a Roomba? Yeah, how many of you have one of those smart refrigerators, right? Or that Nest appliance, or also commonly known as vector for distributed denial of service attack? 3 million smart toothbrushes lead to a DDoS attack. Yeah, welcome to distributed systems, right? How many of you thought you'd see the day when your toothbrush would be on the internet? Yeah. What are some of the problems we face with distributed systems? Well, again, there's only 2 hard problems with distributed systems, right? How many people have run into these issues before? In exactly the opposite order, right? Have you ever actually sat down and tried to figure out how to do exactly once delivery? Ever actually tried to work out the details? How many people have heard of the Byzantine generals problem? This is taking some of us back to our CS days, right? Yeah, this stuff is kind of hard, and frequently what we do is we just kind of make it harder on ourselves. Fundamentally, distributed system is any program which uses resources out of process. Doesn't even have to be a second machine involved. As long as it's going out of process in order to be able to complete its work, it is by definition a distributed system. Now, frequently, you will come back and say, well, okay, if it's running on the same box, we don't have a lot of the same kinds of concerns that we do as if we were trying to do something across the internet, across the World Wide Web, or if we're trying to do something across multiple different wide area networks, et cetera, et cetera. But at the same time, even as a developer, every single person in this room at some point has been working with building a web application, fired up the client, right? Fired up the Angular app or the React app or the Vue app or even the straight up HTML app. And all of a sudden it's broken. It's not doing anything. And you're like, what the hell? I just fixed it. And that's when you realize you haven't started the server process up yet. Even on the same machine, these things can break down very, very, very easily. And so fundamentally here, we can say, practically speaking, that a distributed system is any system in which network access is at the core. But even when it's running on the same machine, right, I may still have a distributed system because there are a number of applications that can work in airplane mode. They do a certain amount of local storage, they do a certain amount of local caching, et cetera. And then as soon as you reconnect to the network, they start updating everything behind the scenes. And that's when you discover that, in fact, something went wrong, something is incorrect, there is some sort of conflict in the data, et cetera. In which case, congratulations, you have a distributed system. It's fair to say that most of the people at this conference, most of the people sitting in this room, most of the people in the industry as a whole are building a distributed system, whether or not they want to admit it. So let's talk about one of the most successful distributed systems in our industry's history, which of course is the World Wide Web, right? Bit of a history. Most of you will probably know pockets of this. Tim Berners-Lee begins his research in '89 at CERN. In 1990, he creates a proposal for a hypertext project. This proposal, by the way, is accessible as a PDF at that particular URL if you want to see the actual thing that really kicked off what we now call the World Wide Web. Interestingly enough, his supervisor scribbled on the front page of the proposal, vague but exciting. Yeah, kinda, sorta. Because what TBL was proposing was there were all these different pockets of information. Can we glue them together into one system in a certain particular way if we set up some basic rules, some foundations, some specifications, if you will, and then anybody can expose this data. And by the way, we want to open it to the public in '91, and CERN actually guaranteed that all of what they were doing would in fact remain open to the public. That is to say, whatever protocols they created, whatever software they created, all of this would in fact be freely accessible to everyone in 1993. Of course, we now know, close to a quarter of a century, or a little bit over a quarter of a century later, the web seems to have succeeded. I don't know about you, but I don't know that I could go a day in my personal life without touching the web in some way, shape, or form, either by browsing it directly or by using applications that in turn make use of that platform to carry out operations on my behalf. The interesting thing, of course, about the proposal is that of the 8 pages involved in the proposal, a full page is spent discussing hypertext. He created a number of things, HTTP URI, which was originally known as URL, HTML, browser, server, etc. A lot of this stuff is still freely accessible if you want to go play with it. And anybody who has tried to replicate the web's success for themselves in terms of creating their own platform has had varying degrees of success, right? We could talk about Twitter. How many people remember the Twitter fail whale back in the day? Yeah, there's all of the Gen Xers in the crowd right there. How many people have only known it as X? Obviously we left all of the young kids at home, right? How many people think that Twitter is more reliable now than it was, say, 15 years ago? One couple of hands. Like, as soon as one hand went up, then a couple of people back like, oh, okay, cool, I won't be the only one. Awesome. Even Amazon in its earliest days, they had their failure moments. Why can't we just do what the web did? This is what many of the proponents of REST, representational state transfer, will stand up and say, yes, that's exactly what we should do. We should absolutely follow what the web did, because the web has clearly been successful. And so if we just do what they did, we will be clearly successful, and we will be able to have the same kinds of success, same kinds of scalability, etc. As a matter of fact, there is a gentleman who agrees with you, Roy Fielding, the creator of REST. And when I say the creator of REST, Roy didn't actually invent a lot of the principles by which REST is known. Roy was the first one to really gather them up, document them, and provide them in a manner for us to consume. And he did this via his doctoral thesis in 2000, which is an interesting thing to talk through. By the way, for those of you who don't know Roy beyond REST, he also was one of the co-founders of the Apache HTTP server. That's how he was so deeply involved. He's been very deeply involved in a number of the other Apache things as well. And in particular, let's see, there we go. I skipped one. How many people have read Roy Fielding's thesis? A couple of hands. How many people have heard of representational state transfer? How many people are using REST today, currently? Okay, stop for a moment. Keep your hands up, keep your hands up, keep your hands up. Number of people using REST, keep your hands up. Look around the room, see how many people are using REST? But there was only about a dozen of you who'd actually read the goddamn manual. This is why Roy Fielding is mad at all of you. And he's not wrong. Because in his thesis, which by the way is remarkably approachable, okay, a lot of the theses and other academic publications that you'll find available for consumption just slathered over with Greek symbols, making them entirely incomprehensible, except maybe to this crowd, now that I think about it. I never really thought about that. You guys might actually be able to understand. It's all weird math kinds of stuff. As a matter of fact, people who have now sort of gotten out of the academic industry have come back and said, yeah, most of the time, the people reviewing these doctoral theses, they don't do the math either. One guy actually put nothing but nonsense in all of his all of his math sections. See figure 1A for a description of the type system. And it was like a cat walked across the keyboard. Literally, he had his cat walk across the keyboard, put that in his thesis, and everybody said, looks great, and approved it. But Fielding's dissertation is a little bit different. Fielding actually doesn't bother with any of that math. What he does do is he walks us through a number of what he calls architectural styles. That is to say, some general principles by which we build architectures. This is the only place, by the way, that I've ever seen architectural style used in any kind of a formal capacity. And I'm actually very much a fan. In chapter 1, he goes through a very definition of software architecture, very general definition of software architecture, because this is what us architects have to do. Whenever we stand up on a stage, we have to describe what we mean by architecture. Whenever we get a part of a team, we have to describe what we mean by architecture. Whenever we meet socially at a bar, hi, I'm Ted, I'm an architect, and this is what I mean when I say software architecture. Because we don't have a really well-defined term that everybody subscribes to. So Fielding does the same thing in chapter 1. Then he goes into a general definition of network-based application architecture, specifically describing what it means to be a network application. That is to say, an application that has, at its heart, a distributed system. In chapter 3, he starts going through a catalog of styles, which he will then reference again in chapter 5. But chapter 3 is a really interesting place to dive in, because there he starts talking about client-server. He starts talking about client-cached server. He starts talking about various operations in terms of code on demand and so on and so forth. He's got about maybe 24 different styles in there. In chapter 4, he describes the requirements for the web. And in chapter 5 is where he actually derives the representational state transfer architectural style. In this particular order, he starts with a null style, which is basically just a starting point, no style whatsoever. And then he goes to client server, he adds stateless, he then adds cache, puts a uniform interface in front of it, makes it a layered system, and has an optional code on demand. And he's even got this lovely little graph where he shows how each style influences the next one. and basically ends his thesis with, this is representational state transfer, and it is basically the architectural style that powers the World Wide Web. Now, the interesting implication of all of this, if we go back and look at some of this, 90% of what we care about when we start talking about distributed systems is really nothing to do with the distribution itself. Do we really care exactly how the bytes flow from one place to another? Most of the time, not really. Most of the time, when the system is 100% stateless, distribution is easy. If I don't have any state that I need to worry about, and that's actually one of the most interesting things about the whole RESTful architecture, the state is the hypertext that's being transferred back and forth. This is where Fielding coins the acronym HATE OAS, hypertext as the engine of application state. So in the case of the web, all of the state is literally being transmitted back and forth across the wire. That's one of the signature characteristics of a RESTful application. Now, when we start talking about building these distributed systems that we have to work with, the things that we have to build, for example, if you're a bank and you're building a distributed system to allow me to check my account balance, if you, in fact, send over everything as a part of a hypertext document to my browser, including, by the way, my password, including, by the way, maybe my social security number. Maybe there's a lot of things, as a matter of fact, that a bank probably shouldn't be sending back and forth across the wire. And we can talk about, oh, it's HTTPS, it's all completely secured, right? We've got this nice perimeter security, right? We can trust in cryptography because nobody will ever actually lose the private keys. How many of you have heard of the PuTTY breach that just happened like a couple of days ago? PuTTY is, in fact, one of those foundational Unix pieces that's used for being able to establish and maintain, secure connections and whatnot. There was apparently a flaw or a leak. I haven't read the details yet. And millions of private keys were potentially made available to attackers. Whoops! Yeah. What the web needed was in fact different from what most of us need when we start building our distributed systems. So we can't just say, save us, Dr. Fielding, and just, embrace HATOS and we're good to go. Because one of the things, again, we go back here, you see that third line down, stateless. Roy Fielding hates cookies. I am not kidding about this. About 20 years ago, I had the opportunity to share a stage with him for a show in Switzerland. And he stood up at that show and he said, I hate cookies. I hate that all of you are using cookies. You are breaking the web. And if you are using cookies, you are a terrible person and you should feel bad about that. I mean, he does not mince words, this man. The reason is because, frankly, the state is entirely contained inside of hypertext, so what do you need cookies for? First of all. Second of all, we lose the whole concept of statelessness if the cookie is in fact something that's holding state on the server, because now we have to do some of that weird magic where we pin this particular browser to that particular server in order to make sure that that particular server has the appropriate thing that the cookie is pointing to. It complicates the whole thing. Because really, the whole thing is about state and state management. And where do we put the state and what kind of state is it, et cetera, et cetera, et cetera. So ironically, as we stand here and talk about distributed systems, we need to start talking about state. Now, fundamentally, there's a couple of things to understand about state. First of all, there is that state which we care about for now, and then there is that state which we care about forever. So as a case in point, if I go up to Amazon.com and I fill out a shopping cart, and for whatever reason Amazon.com loses that shopping cart, maybe they had a server crash, Maybe my session expired and they threw the shopping cart away, whatever. I don't care. They lost my shopping cart. Am I mad? Lots of people actually filled out shopping carts for a long time. Before Amazon had this wish list feature, people would fill out a shopping cart and then take a screenshot or print the page, and that was what they gave to people as a Christmas list. Which is why Amazon said, why do we have so many abandoned shopping carts? And they went out and talked to some folks and went, oh, so if we gave you a wish list feature, which is why they now have that feature. Because the shopping cart itself is transient state. It's state that, yes, we care about, but we don't care as much about it. Because in many cases, it is the result of some processes. It is something that we fetched from some other place. It is data that we calculated from known sources. Or in some cases, it's what the user has filled out, which they are capable of filling out again, even if it's annoying. Don't get me wrong, losing transient state is frustrating, and it's not desirable. But durable state is the state we really care about. Because if I fill out my shopping cart, and then I give you a credit card number, and then you charge my credit card, and then the system crashes, and then I never get whatever it is I ordered, we have a word for that. Fraud. Most people are not real comfortable with just making a, generous donation to the richest man in the world. We want whatever crap it was that we ordered. That's durable state. And the distinction between transient state and durable state is where you start. What state do I really, really care about, and what state can we, if we lose it, yeah, it sucks, but. Once we've determined some of the difference between durable and transient state, second question becomes, where exactly does this state live? Now, we can talk about where it's stored, databases and so forth, and we'll get to that in a second, but where exactly does this state live while I'm working with it? Now, most of the time when we see this state, we see it in the form of variables, bindings, and so forth in our programming language. But where exactly did they get that data from in the first place? One of the things that we have always liked about doing some of the things like command line tools and desktop applications is that all of the transient state is really easy. It's just the local variables in the process as we run. When we go to the web, where in fact each step or each page could in fact be an entirely separate request-response round trip, we have to somehow put this transient state someplace and then get it back. Now, historically, this is what some of the web containers have tried to do for us. Oh, sure. We'll give you this notion of a request object, says the servlet API. We'll give you this notion of a space where you can put this data, and then you can fetch that data, and generally it looks just like a big old hash map, right? Big old dictionary of various things. And all the various server-side web containers, they all do the same thing. That server-side session-held state will in fact be identified because, well, we need some way of identifying who you are coming from the client side, thus establishing the cookie, blah, 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 blah. That is often what I will refer to as context state. In other words, there's some construct, there's some context we have to reach in and grab that state from in order to be able to work with it. And that means that somehow that context has to be married up against my locally executing code. So somehow there's some sort of magic that goes on in the depths of the system that somehow starts from the cookie in the user's browser and turns into a session object or some server-side dictionary where I can go get that context-held state. That's typically where we put the transient state, because again, if we lose it, it's not the end of the world, it's frustrating. But the durable state typically goes into a database of some form. Oops, screensaver. And so now we get into the whole durable state wars thing. What should we put it in? Should we put it in a relational database, in a document database, in a a graph database, right? This is where, the various folks from Postgres are going to stand up and start talking about how they've actually got all these different flavors. Andre just did some bullshit about Oracle and JSON and whatever bullshit he was talking about. People are going to argue about this. Love you, Andres. The point is, it doesn't really matter from our perspective. It is a place of durable state. The end. Now, that state can certainly have a shape to it, and that shape is frequently where we get into trouble with the whole object relational impedance mismatch, or an object document impedance mismatch, or an object hierarchical impedance mismatch, because all these different things have different shapes. And this is where we get all those different libraries that will try to help pound things from one shape into another. And, depending upon how deeply you want to be a purist about it, they do a good job, they do a terrible job, whatever. They store data, great. That's where we want durable state to live, great, because they provide something that the transient state, like the session state on the server, doesn't provide, and that's transactional semantics. The idea that if I write something to a durable state, I know it's going to be there. That's because we need that kind of guarantee for durable state. Now, here's where things get kind of fun. Everything is about state management, right? And one of the states that we have to worry about is the user. Because if, quite frankly, the user were not involved, we could do all of our processing, do all of this state manipulation on some server tucked away in a rack somewhere, and it wouldn't have to go anywhere. And this is what we often refer to as batch processing. If I don't have to involve a user, again, this story becomes very, very easy. Transient state needs to be accessed quickly. I need to be able to get at it in order to be able to process my code. In order to be able to have that performance, I need to be able to look at what the user typed in and validate it in order to make sure that they typed it in correctly. I need to be able to look at what the user typed in and validate it against what happens to be in, if they're looking up, for example, an order, I have to make sure that that order number not only is formatted correctly, but also actually exists. You'll notice that these two things are pulling us in very, very opposite directions. On the one hand, I need to verify that the order number is correct and it's valid and it's in the right format. We want to do that very close to the user. Because how many of you have ever done one of those web forums where they give you like 40 fields and you type stuff in and then you push submit and then it comes back and tells you there's an error on the third field. So you fix that error and then you push submit and then it comes back and tells you, oh yeah, by the way, there's an error on the fourth field as well. So you fix that one and then they come back and tell you, oh yeah, by the way, your dates are formatted wrong. That's the fifth and sixth fields. And you start wondering who exactly was paid to create this and why they got paid and how in the hell the US government always seems to find these people. Moving the state back and forth carries with it a significant amount of the costs that we'll talk about when we talk about distributed systems. When we talk about how much bandwidth is consumed, it's all about this state transference going back and forth. We want to keep a good chunk of that transient state close to the user because then we can do a certain amount of things in a relatively performant fashion so the user can get a decent experience out of it. But we also don't want to keep going back all the way back to the durable state container through however many layers of nodes in the distributed system to get to that durable state to make sure that that order number is in fact correct. And by the way, transforming that data across shapes has its own set of costs. And on top of all of this, configuration data. Now, some of this configuration stuff is a little bit easier. I mean, configuration is itself a form of state. And some of this has been solved because we have Docker and we have Kubernetes and we can bundle the code with the configuration as a single artifact, right? And in some places they're actually saying, oh, no, you don't want to do configuration as state, you want to do configuration as code. That's all the infrastructure as code folks that are pushing that particular story. Once we start establishing in our own mind that all of this is about state management, and we start wrestling with that particular problem, by the way, we also have to keep the fallacies of distributed computing in mind. How many people have seen these before? Oh, if you call yourself an architect and you don't know the fallacies, you need to go back to school, folks. Everyone, when they first build a distributed system, makes the following, oops, not 10, 8, or it's a binary 2, I'm not sure. All turn out to be false in the long run, all cause big trouble and painful learning experiences. The network is reliable. Who believes in that one? I have 2 words for anybody who does. Conference Wi-Fi. Love you, Pat. Right? The network is reliable and will never fail. Yeah, okay. This is a fallacy, though. Because if you genuinely do not believe that the network is reliable, then every single time you make a call that takes you across the network, you will put code around that call to deal with the possibility that the network might disappear. How many of you do that? Couple of hands. How many of you think that's such a pain in the ass? Lots of hands. Which means that everybody who didn't raise their hand when I asked that question just a few minutes before about how many of you actually put error handling code around your network calls, you're just assuming that the network is reliable, right? You're just assuming that the network will never go away. I mean, come on, we're running in the same Kubernetes cluster. We've never seen a partial Kubernetes cluster's failure. We've never seen just one machine in a rack go down. By the way, those of you who ever spent any amount of time in the Java distributed technology space, remember how RMI forced you to catch remote exception every single time you called one of those methods? And do you know how much people whined about that? Lots. And do you know why those remote exceptions were there? Go see fallacy number 1. Because you need to deal with the possibility that the network may not exist when you actually try to reach for it. By the way, how many of you also put try-catch blocks around every single one of your JDBC calls or whatever particular layer you use for, by the way, congratulations, I saw your hand there. You're the only one whose hand came up, so you're winning already. Because yeah, that's another network call. And just because we just successfully were able to execute one does not mean that the next time we go, the server will be there. We could do this 100 times successfully, and that still doesn't tell us anything about whether the next time we make a network call, whether the network will still be there. These fallacies are insidious and terrible and horrible, and we hate them because they force us to spend 80% of our code dealing with a situation that it'll never happen. Werner Vogels, CTO of Amazon, has a great quote. He says, "At the speeds at which we are doing things today, the chance of something happening 1 in a million times is next Tuesday." Right? So here's the thing that you really need to start thinking. If you take away nothing else from this talk, the thing you really need to start embracing is not if there's a failure, it's when there's a failure. When the network fails, what are you going to do? Latency is 0, bandwidth is infinite, the network is secure, topology doesn't change, one administrator, transport cost is 0, network is homogeneous. All of these are blatantly false statements, yet all of these are statements that I can see enshrined in many of the distributed technologies that we use, in many of the ways in which we use them. So one of the things that I started to do when I started thinking about distribution and distributed systems and how exactly do we want to reason about all of these things, because new distributed system tech is coming at us fast and furious, right? You've got GraphQL, you've got gRPC with protobufs, you've got all these different messaging things, streaming, etc. How the heck do we make sense of it all? Because the last thing I want to have to do is I don't want to have to sit down and try to create a project with every single one of them in order to understand the ins and outs. And as I started thinking about all of these, it became apparent that there are certain clusters, patterns, such that we can think about any distributed technology as essentially a three-part tuple. That being channel or the medium over which the communication happens, the wire format, what it looks like on the wire, regardless of whether there's a wire involved or not, while it's in the channel or on the medium, and then the interaction or the exchange. We have a lot of different ways that we can communicate data back and forth. We can certainly sling it over TCP/IP. That's one of the core things that we use all the time. We can also do UDP/IP. And if you've not heard of UDP/IP, you haven't spent much time in the game development space, because this is what they like to use, predominantly because UDP/IP is faster than TCP/IP. Anybody know why? There's no guarantees, right? TCP/IP is a technology that will guarantee, as best as it can, that a message was delivered. So if I write something on an index card and I hand it to Andres and say, yeah, by the way, this needs to get to somebody in the back row there. Well, Andres is going to say, okay, I've received your index card. And I say, okay, I've received the fact that you have received my index card. And then Andres is going to turn to the person next to him and say, this index card needs to go to that person in the back row, and hand the index card over. And that person's going to say, I've received your index card. And Andres would say, I've received the fact that you have received my index card. Meanwhile, UDP is like, yo, dude, this is what I want you to know. And if they're listening, what do I care? This is Greece, after all. You people shout at each other all the time. You don't actually expect to be heard, do you? Right? That's UDP. UDP is great because it just shouts into the ether, and if you get it, great. And if you don't, we'll move on. And sure, 98% of the time you're going to get it, and the 2% of the time you don't, we call it lag. Now, those two technologies in themselves already have some really interesting foundational dynamics that are different to them. Because TCP/IP is great for making sure that messages get somewhere. Because in fact, if for whatever reason, if Andres can't hand it to the person behind him, he can try a different node. This is kind of how TCP/IP was originally created, to be able to route itself throughout the grid in order to be able to reach its destination. That's what creates some of the self-healing nature of the internet. But all of that comes at some cost. So if we're trying to replicate what we're doing right here, right now, where I'm just basically shouting out into the ether, and yeah, there's probably some people in the back there who are playing solitaire, and I don't care. I get paid the same regardless whether you were paying attention or not. This is very clearly UDP. But if we were to do this TCP/IP, I would have to go over and say, okay, I'm going to give you a lecture for 40 minutes. And then at the end, you're going to say, I got it. Right? Say, I got it. Say, I got it. I acknowledge that you got it. Now I'll go to the person on your right who is really trying hard to avoid eye contact. He really does not like being singled out. Yeah, this is going to suck, because if I have to do a 40-minute lecture through the first row, hang on back there, I'll get to you eventually. Speaking of being here for 3 days. TCP/IP is terrible for doing this kind of broadcast thing. So the channel matters. Now, we can also talk about using alternative channels like the file system or Unix pipes, or in some cases the database. There were a number of messaging systems that were built over the years that actually basically stored on top of a database table. There was a period of time in the 2000s, 2010s, when messaging middleware was such a big part of the discussion at the time. And so you had all these database vendors who were like, yeah, we're a messaging system too. You just call this stored proc, and we store your message, and then somebody else calls to fetch the message, and we give it to you. Meanwhile, under the hood, it's like select star from table where. But that's our channel. Next, we get to the wire format. The wire format is really going to tell us our degree of interoperability, right? Where the channel is going to tell us a great deal about our performance and to a lesser degree our scalability. This is really going to talk about our interop. HTTP, for example, as a protocol, is deliberately designed to be as interoperable as possible by mandating that all of the HTTP protocol features must be in 7-bit ASCII clean text format. This is because that is literally the lowest common denominator amongst most of the computer systems in the world, okay? And so therefore, it made it that much more approachable for other platforms to be able to write their own HTTP clients and servers. Now, some would have you believe that JSON is in fact the best interoperable format, not just because their database/boss sells it. But yeah, there's a certain elegance to JSON, right? It's a nice hierarchical format, and it has curly brackets. Don't underestimate the importance of curly brackets, because when we tried to do a hierarchical format that didn't have curly brackets and instead had these sharp pointy brackets, we didn't like it. Still doable, still very powerful, but we didn't like it. And of course, we could always do it in binary, but now we have to agree on which end comes first. Are we big endian? Are we little endian? Who has time for that? The other thing we can get into is the interaction, the exchange. Who talks first? How exactly do we do this? See, one of the interesting things about most of the technologies with which we as architects are familiar is that they operate in a request-response format. Think about HTTP for a moment. I hang out on the server. I'm the HTTP daemon. I'm just doing nothing. I literally am doing nothing here. And then somebody out there says, hey, I'd like to request a page. So they initiate the communication. They open a connection to port 80 on my machine, and they say, hey, fetch me this resource identified by this particular URI. And I say, oh, okay, cool. Let me grab that for you and throw it down the pipe. And now I'm back to hanging out. Now, what happens if, in fact, the client out there wants me to tell them when something happens? Well, this is where a request-response driven protocol is completely at its worst. Because either you have to request every so often, that classic polling loop that we go through, and I just keep saying, yep, nope, nothing, nothing. Are we there yet? No. Are we there yet? No. Are we there yet? No. You love it when your kids poll, right? That's always such a great feeling to know that they're still alive back there, because they keep asking you, are we there yet? And what do you as a parent do? First of all, you take a very strong grip of the steering wheel. Then you tell them, I'll tell you when we're there, right? In other words, I will initiate communication with you to tell you that something about the state of the universe has changed that you are interested in. This is solicit notify pattern. And it's actually really tricky to accomplish in a lot of our technologies unless we invert who the client and the server are. Go look at any of the classic webhook implementations. What are they doing? They're basically saying that the client is now the server and the server is now the client, but otherwise it's just HTTP. So we can take pretty much any of the distributed technologies that we see in the world today, and we can break them down into this tuple. And you'll notice, first of all, that a lot of the really common ones, right, request response, request response, request response, request response, there really isn't anything that does solicit notify unless, again, we somehow invert the client-server relationship and say that now the server is itself a client. By the way, those of you who are thinking of what about something like WebSockets, well, a WebSocket connection is essentially an HTTP request that resolves down to a TCP/IP socket. And from that point forward, it's fully bidirectional and you can treat it just like a socket. A couple of the other things that need to be discussed when we start talking about distributed systems, how exactly do the components know about each other? When I go to my browser and I type in www.amazon.com, how exactly do I get connected? Well, this is DNS, right? And if anything goes wrong, it's always DNS, because it's always DNS. But the domain name service is itself a dynamic registry of these things. It's essentially a lookup so that I don't have to know ahead of time where all of the components are. And if Amazon's server goes down and they replace it with another server someplace else, or if they in fact have a server that's closer to you, there's negotiation that takes place here that allows us to be able to reach out and find a server, either the backup one because the primary one went down, or something that's actually closer physically to where we are at. This is a powerful tool for creating resilience. And in many cases, we don't spend any time thinking about how do we locate the components. We just always assume they'll be there because, again, the network is reliable and machines will never fail. By the way, when they fail, how do they restart? Many of these services will have little watchmen that will sit around and reboot it in the event that it goes down. But what does that do in terms of the state that was held inside of there? Again, I'm not coming in here with any answers. I'm not telling you this is the one distributed system technology that you should use for all of your projects here on out. What I'm doing is I'm literally giving you some of these questions that you can ask yourself as you start examining all of these technologies. Where is the transient state? Where is the durable state? What is the shape of that state? And how do I want to store it? How do I want to partition it? How do I want to access it? And if you can answer all of those questions, congratulations, you're an architect. Peace.
Thank you, Ted. Amazing talk, very interactive. Do we have any questions? No? Okay, so Hala, are you with us for throughout the conference?
I'll be here tomorrow. I'm doing how to build a virtual machine, like a bytecode virtual machine talk tomorrow morning.
Great.
And so I'll probably be here throughout most of the day tomorrow. Saturday, though, it's Greece, baby.
Somebody also told me they want to have an interview with you. So
they have? They've told you that?
Yes.
Okay, cool.
So if you're up for it?
I'm sure.
Let me take you there.
All right.
Great. Short 5-minute breaks and we'll be back here.